Here's another example where we can compute the differential. Remember, we're looking for change in outputs is going to be not just slope, but a slope matrix. We call that the total derivative matrix, or the matrix that's made up of all those partial derivatives times the change in our vector of inputs. This particular function has two inputs, u and v, and then it has three outputs. We can think of those as x, y, and z. So this is a parametric surface that we're talking about here. Okay. So what we want to do is to calculate, let's see, the change in output, df, right, is going to be the change in the three outputs. So we could say dx, dy, and dz. And now the total derivative matrix has to be a 3 by 2. It has to be 3 rows because there are 3 outputs. There have to be 2 columns because there are 2 inputs. So u and v. So we're thinking about, okay, if we make a change in u, then that should multiply derivatives with respect to u, and the change in v should multiply the rate of change with respect to v. So let's look at the derivative of x with respect to u. That's 2u. The derivative of x with respect to v is 0. The derivative of y with respect to u is 0. The derivative of y with respect to v is 2v. The derivative of, I don't know if I called that, that's z. Right? The derivative, oh dear, I did. Okay, dz. Okay, so the derivative of z with respect to u is 1, right? The derivative of this with respect to u is 1. The derivative with respect to v is negative 1. So this is what we call the total derivative. Here, just has all of those derivatives, right, organized in such a way that we could take the vector of changes in input and multiply them by this total derivative matrix, and that would give us the individual changes in output for our function. So we could do this. We could find the linear. We could use this. We could find the linearization, or the tangent space, of our function bold f near some particular point. Let's do it near some point like where uv equals 3, negative 1. Okay. At that point, let's see, when u equals 3 and v equals negative 1, x equals u squared, so that's going to be 9. Y equals v squared. If v is negative 1, then y will be 1. And z is u minus v. 3 minus minus 1 is 3 plus 1. That's 4. Okay, so we can say the change in x, so how far x moves away from 9, the change in y, how far y moves away from 1, and the change in z, how far z moves away from 4, is going to be equal to our total derivative matrix. Let's see, if u is 3, then this is 6, 0, 0, negative 2, because v is negative 1, and then these were constant already, and then change in u would be how far u moves away from 3, and change in v would be how far v moves away from negative 1, so v minus minus 1 would be v plus 1. This now gives us a set of 3 linear equations. They're actually the best linear approximation to each of these 3 equations. So we find that, let's see, this one says that x is equal to 6 times u minus 3 plus 9, right? Because x minus 9 would be this number times u minus 3 and 0 times v plus 1. So I just got x alone by adding 9 to both sides. Let's see, y is going to be equal to negative 2 times v plus 1. Let's see, and then I'm going to add this one. It was y minus 1, so add that over to the other side. And z equals, let's see, 1 times u minus 3, so that's going to be u minus 3, minus 1 times v plus 1 is going to be minus v minus 1, and then plus this 4. Notice that that simplifies to be just, since we have negative 3 and negative 1 and plus 4, that simplifies to be just u minus v. Okay, so each of these functions is now linear. Notice the function for z is actually what it originally was, because originally the function for z was linear, and so we found the best linear approximation to some linear function is just the linear function. Okay, so we have these linearizations. I could actually simplify this a little bit. Let's see, this would be 6u minus 18 plus 9. That would be 6u minus 9, right? Negative 18 plus 9 would be minus 9. And negative 2v minus 2 plus 1 would be negative 2v minus 1. So we have our 3 linear equations. Let's see what that does. Both of these are parametric surfaces, right? Because both of them have 2 inputs and 3 outputs. So what we could do is to graph those parametric surfaces in Maple and look at what we get. So since these are parametric surfaces, I can just enter the parameterization here. let's see, so plot 3D, and then we have u squared. The next function is v squared and u minus v. And we just need to put bounds on u and v that contain our center point. Let's see, we were at the point 3, negative 1, so the bounds on u should include 3, so we can be in that region. How about from 2 to 4? The bounds on v should include negative 1, so how about from negative 2 to 0? Then negative 1 will be right in the center of that range. All right, and we'll do the same thing for our linearization. Just give that plot a different name. But now the linearization of x is 6u minus 9. So 6 times u minus 9. The linearization of y is negative 2v minus 1. So negative 2 times v minus 1. And the linearization of z was the same as it was before. So I'm plotting both of those surfaces in the same range. Let's see what we get. All right, yeah, so we got, this is the original parametric surface, the one that is nonlinear, and then we have the approximating tangent plane, right? And right in the center there where we did our approximation, this is where the point 3, negative 1 is. This is when you plug in 3 for u and negative 1 for v, this is where you are. You can see that the tangent plane does an excellent job of approximating this bendy nonlinear function as long as you don't go too far away from that center region. Let's do another example. This time we have a parametric space curve because we have 3 inputs. You could again think of those as x, y, or sorry, we have 3 outputs, x, y, and z, and 1 input, t. So it's a function from r to r3. That's a parametric space curve. Let's compute the linearization. So dr, since r consists of 3 things, the change in r would be a vector of changes in x's, changes in y's, and changes in z's. And now our total derivative matrix, this time since there are 3 outputs, the matrix has to have 3 rows. There's only 1 input, so the matrix only needs 1 column. And that 1 column, there's only one thing to change, right? All we can change is t, so we'll write dt here. Okay, well the derivative of x with respect to t is 1, so that goes here, because dx would be the slope in the x direction times the change in t, or the slope of x in the t direction times the change in t. The derivative of y, the derivative of cosine, is minus sine t. And the derivative of z, the derivative of sine t, is cosine t. So this gives us our differential. If we had a particular value for t and we were thinking about changing t by some amount dt, then we would just multiply that change in t times this vector evaluated at a particular time, and that would give us an approximation to how much x, y, and z are going to change. So if we wanted to find, let's say, find the tangent space, in this case since it's a line, the tangent space will be a line. Since it's a curve, the tangent space will be a line. Find the tangent space near or at, near, let's see, t equal, what should we do? Maybe t equal 3 pi fourths. Okay, when t equal 3 pi fourths, then the value of x is t, so that's 3 pi fourths. The value of y would be the cosine of 3 pi fourths, which is negative root 2 over 2, so that's y. And the value of z would be the sine of 3 pi fourths, which is root 2 over 2. So we get change in x would be x minus its center value, 3 pi fourths. Change in y would be y minus root 2 over 2, so y plus root 2 over 2, and z minus root 2 over 2. That is going to be equal to our rate of change matrix here, which is 1. The sine of 3 pi fourths is root 2 over 2, so this is negative root 2 over 2. And the cosine of 3 pi fourths is negative root 2 over 2. So these are what my values of my slope near 3 pi fourths. And then change in t would just be how much t moves away from that center point, 3 pi fourths. So we get now 3 equations. The first one says x minus 3 pi fourths equals t minus 3 pi fourths. So the first one says x equals t. This was already a linear equation for x, so the linearization is also that same thing, right? It's that same line. But then y is equal to negative root 2 over 2 times t plus root 2 times 3 pi fourths over 2, so that makes root 2 times 3 pi over 8. And then moving the y had a plus root 2 over 2 on the side. To move it over, we get minus root 2 over 2. Z works similarly. We get negative root 2 over 2, so negative root 2 over 2 times t, and then negative root 2 over 2 times negative 3 pi over 4 makes plus root 2 times 3 pi over 8, and then getting z alone would require us to add root 2 over 2 to both sides. So what we found are linear equations for x, y, and z that do a good job of approximating these nonlinear equations when the value of t is near 3 pi fourths. So we can visualize this. This is going to create the tangent line for our curve at our given time, at time 3 pi fourths. So let's graph it in Maple and see what we get. So the command in Maple is going to be space curve. So we're going to use space curve. So the first plot will be my nonlinear function, so space curve, and the function is t, cosine t, sine t, and we want to make sure we include 3 pi fourths in our range for t. So how about we go from pi halves to pi, and 3 pi fourths will be right in the middle there. And I'll do the same thing, only I'll do the linearizations for my second plot. The linearization of t is t. We found that the linearization of y would be negative root 2 over 2 times t. So negative square root of 2 over 2 times t, plus 3 times pi times the square root of 2 over 8, plus 3 times pi times the square root of 2 all over 8, and then minus root 2 over 2, minus the square root of 2 over 2. Okay, so that's my linearization for y. The linearization for z was similar. So I'm just going to copy it and paste it in here. The only thing that changed was, I think instead of having a minus, we had a plus, right? Looking at the two linearizations, they're identical except for with the y there's a minus, and with the z there's a plus square root of 2 over 2 on the end. Get rid of that extra comma, and we should be good. Okay, and we see it. If you look here, we have the nonlinear curve, right? So that's the original nonlinear function. That's actually a helix, and what we've created when we found, we used the differential, right? We evaluated the slopes at a particular point, and then we were able to get this tangent line to the curve. So this is the best linear approximation to the curve near the time t equal 3 pi fourths.